Good morning, students. Today we are going to discuss an important concept in machine design called design for static load or steady stresses. Before going into the design equations, let us understand a simple question. What happens when we apply a load to a machine component? For example, imagine a bolt connecting two plates. If the load acting on the bolt remains constant, the bolt experiences a nearly constant stress. Similarly, consider a bracket supporting a fixed weight. If the weight does not change with time, the load is called a static load. Today, today we are going to discuss. So today's class will mainly answer three questions. First one is what is a static load? Second one, what is steady stress? Third one, how do we design a machine component safely under a static load? A static load is a load that remains constant, does not change with time. Let us take a simple example. Suppose a machine bracket is supporting a 500 Newton weight. If the weight remains 500 Newton continuously, then load 500 Newton is equal to constant. Therefore, this is a static load. The another example is a stationary structure carrying a fixed load. Now compare this with a rotating shaft. A load acting on the rotating shaft may change continuously as the shaft rotates. That is not a simple static loading condition. So remember, static load, that is nothing but a load remains constant with time. Questions to students. If the machine component is carrying a 1000 Newton load is constant, it is a static load? Yes, it is a static load. If a machine component is carrying a constant 1000 Newton load, then it is a static load. When a static load acts on a machine component, it is produce stress. The stress produced by the static load is called steady stress. Steady stress. We can understand this is as a static load or steady stress. For example, consider a rod subjected to a constant tensile force. If load P is equal to 10 kilonewton and the cross sectional area is equal to A, that is 100 mm square, then tensile stress is P by A. So stress is equal to 10 kilonewton divided by 100 area mm square. So you convert your kilonewton into Newton. So 10 into 10 to the power of 3 Newton divided by 100. It gives 100 Newton per mm square. That is nothing but 100 megapascal. Since the applied load is constant, the stress also remains constant. Therefore, we will call it is steady stress. Types of stress. Students, static loading can produce different types of stresses. There are 5 types of stresses. One is tensile stress, second one is compressive stress, third one is shear stress, fourth one is bending stress, fifth one is torsional stress. Let's understand each one. Tensile stress. When a component is pulled, the tensile stress is produced. Example, tie rod. The two ends of the tie rod are pulled away from each other. So this is called tensile stress. What is compressive stress? The compressive stress, when a component is pushed or compressed, then the type of stress is called compressive stress. In that, the compressive stress is get produced. What is the best example? Column. The load acts downward and compress the column. That is called compressive stress. Third one is shear stress. When the two forces try to slide one portion of the component relative to each other, then the shear stress will be occur. What is the example? Bolt or riveted in a joint. That is the best example for shear stress. The fourth one is bending stress. When a beam or shaft bends due to an applied load, in that the bending stress will be get developed. Example, simply supported beam carrying a load. Simply supported beam carrying a load. That is the best example for bending stress. Fifth one is torsional stress. When a shaft is subjected to torque, the torsional stress develops. Example, power transmission shaft. So students, remember this simple sequence. Pull, there is a pull. So due to pull, the tensile stress will be get created. Push, due to push, the compressive stress will be get created. Slide, so due to slide, the shear stress will be get created. Bending, so the bending stress will be get created. Twist, so the torsion test will be get created. This is the shortcut method to remember the simple stresses. Then objective of static design. What is the objective of static design? Why do we perform static design? The main purpose of static design is to make machine components safe and strong. The main purpose of static design is to make machine components safe and strong. Our main objective is to prevent failure, breaking, and excessive deformation. For example, imagine designing a shaft. You imagine designing a shaft. If we select a shaft diameter that is too small, the shaft may fail when the load is applied. When the load is applied. Suppose we select a sufficiently larger diameter, the shaft can safely carry the load. Therefore, machine design or mechanical design is basically a process of answering what should be the size and material of the component so that it can safely carry the applied load. First one is material selection. The another important aspect of static design is material selection. The material should be selected based on strength and working condition. This is also highlighted. For example, suppose we are designing a machine shaft. We may consider material such as mild steel, carbon steel, alloy steel. But we cannot select the material only based on strength. We should also consider the actual working condition of the component. For example, temperature, load, environment and type of application. Therefore, material selection is an important part of machine design. Material selection is an important part of machine design or mechanical design. So, during material selection, we should also consider the actual working condition of the component. What are the working condition? The temperature, load, which environment the material going to be adapt, and type of application. Which type of application the material is going to be used. So we want to analyze all those things, and based on this application we select the material. Then what is mean by factor of safety? Now we come to a very important concept, factor of safety. Students, in real machines, the actual load may not always be exactly what we calculated. That will be get vary. There may be we consider loading, material properties, manufacturing, dimensions and operating conditions. That's why we introduce factor of safety. What is the basic relationship is factor of safety is nothing but strength by working stress. For example, suppose material strength is 300 megapascal and working stress is 100 megapascal. Then factor of safety is equal to 300 divided by 100. So it will give 3. So the factor of safety is 3. Suppose the material strength is 250 megapascal. The working stress is 100 megapascal. Then the factor of safety is 250 divided by 100. It gives 2.5. So the factor of safety is 2.5. This means the design has a safely margin between the working condition and the material strength. What is meant by allowable stress? Now let us understand another important term, allowable stress. The working stress should always be less than the allowable stress. The working stress should always be less than the allowable stress. For example, if the allowable stress is 120 megapascal and the calculated working stress is equal to 80 megapascal, then the working stress should be always be less than the allowable stress. So allowable stress is 120 megapascal and calculated working stress is 80 megapascal. So in this condition, the working stress is less than the allowable stress. Therefore, the design is acceptable based on this criteria. Whether you can design any shaft or some other product, the allowable stress is the working stress should always be less than the allowable stress. Then the shaft or any component can be safe. Suppose the working stress is 150 megapascal, the allowable stress is 120 megapascal, then the design is not acceptable because your working stress is more than your allowable stress. So we want to seriously look in on it. Always the working stress is always less than your allowable stress. We have to increase the component size, select a stronger material or otherwise modify the design. What are the practical applications? The static loading is commonly considered while designing many machine components. The static loading is a